Alrighty then, we have moved on from percent composition, figuring out the percentage by mass of elements in a compound, to a concept known as the empirical formula. And as we see over on the right-hand side of the page here, the empirical formula is, the lowest whole number ratio of elements in a compound. My circling skills leave a little bit to be desired. So, this will not necessarily be the same as the molecular formula, which would be the actual formula of the compound. We'll see an example of this right after this podcast. But it does represent the lowest whole number ratio of elements in a compound. When you think about it, this makes sense because you can have half an atom in a compound. So we have to make sure that at the end we have subscripts that are whole numbers. So the first thing we're always going to do when we're solving an empirical formula problem is we're going to set up a chart. Now, I learned this from one of my chemistry teachers many years ago, and I think it's the most useful way to organize your thoughts when you're trying to figure out an empirical formula. There are ways to do it, but the better you organize yourself, and I honestly believe this, the better off you're going to be. So, I'm going to go ahead and make this chart. It's going to take me a minute here, but I'll explain what I'm doing. So, I'm making a column for each of my elements. Now, let me just read the problem before I go too far. It says that a compound that you found in your basement was analyzed and found to contain 13.5 grams of calcium, 10.8 grams of oxygen, and 0.675 grams of hydrogen. What is the empirical formula of the compound? Now, in this case, you would be given either a percentage or a mass. You can use either one in exactly the same way. If you're given percentages, you can just assume that you have 100 grams of that material and operate in the same way as if you were given masses like we are here. So, I'm going to make 3 columns. One for calcium, one for oxygen, one for hydrogen. Now, generally, you just write them in the order that they appear in the problem. So that's exactly what I did here. Now, the first row in this chart is going to be either the percentage or the mass. Again, we can use them interchangeably. We're given masses here, so we're just going to use them. We don't need to convert anything. So, we have 13.5 grams here. We have 10.8 grams of oxygen, and then we have 0.675 grams of hydrogen. Again, these numbers would be given to you. So, the next step, the next row in our column, is the molar mass. So, once we look up the molar mass, and for calcium, it's 40.08. For oxygen, it's 16. For hydrogen, it's 1.01. Once we look these up, we're actually going to figure out the number of moles. That's the next step. And I'm going to put this in red because it is a rather important step, because this is one of the steps that we need to take to get a mole ratio. So, if we're given a mass and we have the molar mass, we can use those to figure out the number of moles. As we learned several weeks ago, anytime you're given a mass in grams, the conversion factor that you're going to use to convert to moles is, in fact, the molar mass. So since we have that all set up for us, I'm going to draw a line right here. And that line reminds us to divide the mass by the molar mass to get the number of moles. So when we do that, we get 0.336 here. For calcium, we get 0.675 for oxygen, and we also get 0.675 for hydrogen. Now, the next step requires us to get a mole ratio. I'm going to write that down here. And what we need to do to get that mole ratio is a little interesting, because in order to get a mole ratio, we want one of those numbers to be exactly 1, and we want all of the other numbers to be something greater than 1. 1, 2, 3, whatever. And so what we're going to do to make that happen is we're going to divide by the smallest number of moles. So we're going to look at the row above, the number of moles. And we're going to figure out which one has the smallest number of moles. I hope you can see by now that it's the number of moles of calcium. So we're going to divide all of these values by 0.336. So when we do that in the first column, we obviously get 1 mole of calcium. When we do that in the second column, we get about 2. It's probably 2.02 or something like that. If it's that close to a whole number, you can safely round. If it's something like 2.5, you'll need to go an extra step, and we'll go over that later. Now, hydrogen, we have the same calculation, so it's approximately 2. So we now have a mole ratio. Now, if in this last step we did not have all whole numbers, for instance, if one of them was 2.5, we would need to either double, usually doubling works, or triple our coefficients until we got whole numbers. Usually there will be something like 1.5 or 2.5, and you'll just have to double it, and then you're done. Try that first, and if it doesn't work, we can go from there. But generally, that's all you're going to need to do. So these numbers right here in the mole ratio, in this last step here, are the coefficients, or not the coefficients, but the subscripts that we're going to put into our empirical formula. I usually like to abbreviate the empirical formula EF, and we see that we have a subscript of 1 for calcium, we have a subscript of 2 for oxygen, we have a subscript of 2 for hydrogen. Now, some of you who are a little more experienced with using polyatomic ions will recognize that OH is actually a hydroxide ion. So we could also write this as CaOH in parentheses and a 2 on the outside. That is technically the correct formula. If you were to give me the one that's on top, the CaO2H2, that would be perfectly acceptable because you're not really asked to find the actual formula of the compound in this case. You will be asked to find the actual formula of the compound, but we'll save that for a later podcast.